So good morning, good afternoon, good evening to everyone. My name is Melike Erol Kantarci. I'm a Canada Research Chair in AI-enabled next-generation wireless networks and an associate professor at University of Ottawa. I'm also the Director of Network Systems and Communications Research Lab, NetCore for short. So our research is mostly on AI-enabled wireless networks. So using machine learning techniques to design the next generation algorithms for the 5G, beyond 5G and sixth generation networks. And that's why the title of this talk is AI-enabled wireless networks, a bridge from 5G to 6G. We see AI as a great enabler for the next generation of wireless networks. I'll start with this in this talk by first introducing the machine learning techniques that we refer to, that we use, consult a lot of the times. And then I'll talk about 5G and 6G systems, then introduce you a couple of the interesting recent research that we did. And after this talk, Mr. Medhat El-Sayed will talk about more details of these schemes that we developed and published recently in IEEE journals and conferences. So I'll start with a quick discussion or some ideas about human intelligence, because that's what AI field has been trying to do for many years. Actually, most of the ideas that are in AI or machine learning algorithms have been around in the domain of psychology as well. And one of the ideas that is important that we use a lot in our research is the interactive learning of humans and animals. So many of you might be familiar with the psychological trial and error kind of works of Pavlov or the others. So the general idea here is that humans or animals too are not born with a handbook saying what to do and what not to do. So we learn by experience. We try, like touch a hot surface, and then we notice it's too hot, and next time we don't basically touch. So if you look at the AI history, first expert systems were very popular, where the researchers started thinking that if we were able to teach everything to a machine, then they would become intelligent. But this interactive learning is a different point of view. It's that a human learns by interacting. He or she doesn't know all the rules, but they can learn in time. So experience is very important. Now, in the history of reinforcement learning, of course, I mean, those psychological trials go back many decades than the time I have in this graph. But the roots, the formal roots, and the connections with the optimal control theory was driven around 1950s by Richard Wellman. And we still use his Wellman equations in many of the reinforcement, in the foundations of many reinforcement learning techniques. And that was a popular topic at the time, reinforcement learning. And a familiar face from information theory, Claude Shannon, even he had some experiments in 1952 with a mouse trapped in a maze. And he was sort of suggesting directions to the mouse with using relays. So we have Claude Shannon here because, not because he contributed maybe majorly to the machine learning literature, but it's interesting to see a figure from information theory getting interest in that topic and contributing to the area. When we come to 1960s, we see Marvin Minsky as an important figure who has studied the credit assignment problem, which is a very important part of reinforcement learning. And I'll talk about why this is important in a few slides later. Of course, there are many other important researchers that I'm not able to mention right now, but I'm just referring to some milestones in years and some very few researchers who had made breakthrough contributions. And in 1970s, we see Harry Clough actually coming out with the notions that I mentioned to you a bit earlier about the difference about expert systems and how learning should be interactive, or we should not ignore the interactive part of learning. And his ideas influenced Andrew Barton and Richard Sutton. For many of you who are interested in reinforcement learning, you will be familiar with their very famous book as well. In 1980s, they did a lot of research in this area. Around 1989, Chris Watkins made an important contribution, and this was in the domain of temporal difference equations and definitions. And this was important because up until now, most of the problems were model-based, but he introduced the notion of temporal difference, which helped us wrestle with or deal with problems that are not easy to model, and wireless networks is one of them. And of course, after these breakthrough research works in 1990s, we started seeing a lot of game-playing machines, like in this example, Gerald Tassura from IBM with the TD Gammon, a backgammon machine that came, chess-playing machines, Go-playing machines. They are all very they have been very popular since that time and very popular in our time as well. So those are a couple of areas that helped advancing reinforcement learning a lot. And then when it comes to 2000s, of course, it is almost inevitable when there is such a big, exploration, discoveries in one field, that networks would be isolated. So there are some prior initial works who explored the use of RL in computer networks, in wireless, but they were very preliminary, very early works. And even the area of reinforcement learning and deep reinforcement learning, which is something we will talk a bit later, was not well developed at the time. So let's go step by step and talk about reinforcement learning first. So the idea behind reinforcement learning is that we have an agent and we have an environment. We may know the model of the environment, or we may not know the model of the environment, but the agent will take an action. It will cause the environment to change from one state to the other, and in return, it would receive a reward, as we see over here. So the agent will get a reward. This rewarding mechanism is crucial and very important because it will teach the agent how it is doing. Without a rewarding mechanism, there's no way the agent can evaluate its actions. So it's like humans, like touching a surface, it's hot, like you feel that pain, that can be considered like a negative reward or a penalty, or you do something good and you receive a reward. So this is how interactive learning is actually enabled in humans and animals. So the same is being considered for agents here. Now, of course, when an agent is taking some actions, receiving rewards, it might be also like not like a one-time game or one-time action. There might be a sequence of actions. And once following one path or one sequence of actions may lead to the other. And this kind of behavior, like I show in over here in this subplot, happen a lot in games. So like when we are playing chess as a human being, we may follow one of the other strategies. And like when you move your knight in a certain position, then there opens up whole other new opportunities or risks, right? So every action on the board will lead to certain other policies to be developed. And in the end, if you are winning, you get a good reward. If you're not winning, you don't get a good reward for your actions. So you have to go back and see how much reward you can get out of it. So this picture, for example, shows like how policies can branch out. And out of these branched out policies, we can select one that is good. And that goodness is basically the cumulative rewards. It has to have a numeric value so that our algorithms can work on it. So to be able to describe this numeric reward, I have to start explaining the mathematical foundations of reinforcement learning, which are rooted in Markov decision processes. So let's talk about the common definitions of Markov decision processes and then look how reward is calculated. So ST denotes the state of an agent at time t. AT is the action of an agent, action taken by an agent at time t. When we are in state ST, an action AT is taken, in the next clock, time interval, we get a reward. The agent gets a reward of RT plus 1, and the state changes to ST plus 1. Now, if we are in a deterministic environment, we would know, like given the state and action, we would know the probability of ST plus 1, of receiving or of landing into ST plus 1 state. But if the environment is probabilistic, stochastic, then this probability either needs to be known or calculated. So for deterministic environments, we are not concerned with this. We don't have to include this probability into our formulations. But for other type of environments, we need to include, and in some environments, we may know these probabilities, and some environments, we may not know this probability. Similarly, this is the same for the reward. For the same action, an agent might be receiving different rewards over time. Like in a slot machine, once you pull a lever, you may get the same reward, or the reward might be different in each time slot. And then episode is the trial of actions from initial state to goal state. So when we are playing a game from the beginning to end, there will be a set of actions. And then the policy defines the agent's behavior, and it's a mapping from states to actions. And in the end, what we try to find is the optimal policy, so optimal path an agent needs to follow to get to the winning situation. So let's keep formulating these. So a policy is, as we said, a mapping between states and actions. And luckily, the policy has a value. So we can like give some numbers, assign some numbers to the rewards. And by using that, we can come up and say, oh, this policy has a value of 10, this policy has a value of 15, so that we can compare one policy to the other. So the calculation of this value is dependent on the reward values. The calculation of the reward depends whether we are working on a finite problem or an infinite horizon problem. So this formulation is given for an infinite horizon problem. Like we have 3 dots here saying that the rewards goes to infinity, as you see here. So in such a problem, and this is like the common type of problems that we think of, we work on, we don't want to give too much weight to the reward that's going to happen, let's say 10, 20 steps or 100,000 steps later, because that's too far away. We can't really decide, make a good action at that moment if we start thinking about, 1,000 sections later. So we have to be a little bit myopic. We have to give more weight to the actions or the rewards that are happening closer to the decision time, and then the less weight to the others. So this gamma helps with this. Of course, this gamma is between 0 and 1. So this is like a discount factor. So over here, we multiply rewards, the future rewards, by a discount factor, making sure that their weight, their impact on the cumulative reward expectation, and as a result, will give us the value of the policy, will include less of a weight of future rewards. Now, once we have this policy, value of a policy, now the thing to look at, optimal policy, so the value that maximizes this policy. So V star that we see in the Bellman equation, so that's where Richard Bellman comes into the picture, is the optimal policy at ST plus 1. Multiplied by the transition probability. So we're thinking about a general model here where the environment may have maybe stochastic, and we have given the state ST and action AT, we might land on the state ST plus 1 with some probability. These future ones are discounted with a gamma value, and we have the expected value of the current reward. Again, if the rewards are stochastic, then we have to use expectation here. And finally, we want to find an action that maximizes this all these values. And V star ST will be the optimal policy. Now, that probability about environment state, the one that we had in this formulation, this P, over here is a bit tricky. So most of the problems, or not most of them, but some of the problems that people have worked on in AI and machine learning literature was model-based. So the model of the environment was easily obtainable. And the solutions to a model-based environment is sort of straightforward, or is it easier than the model-free environments? Because when you look at this, when the previous Bellman equation, it can be coded in a recursive way, and by using dynamic programming, a solution can be found easily. But the problem is when the environment is not known, so it comes to model-free learning. And the famous model Q learning, one of the famous ones, is Q learning. So Q-learning, we're not going to talk about all the other techniques. I'm just going to mention one technique, and then the others are more or less based on the same principles. Q-learning uses temporal difference equation, which is the idea that comes from Watkins, that's like also like has a correspondence to the real world problems. Like you touch a hot surface, or you say it's hot, then you go a little bit colder, then you look at the difference, and then you make that adjustments. So the Q values are adjusted by looking at the difference, calculating like how much closer we're getting to the higher rewards, how much we're getting away from the higher rewards. And it works with an assignment operator to the actual updates of the Q values in state ST and action when action AT is taken. So, so far this is like the fundamental thing, and I did not mention about this alpha. This alpha is the learning rate. So how much steps do we want to proceed? Do we want to like jump steps ahead where we might miss some of the information for learning, but that will be a fast learning approach? Or do we want to keep those steps smaller, like in smaller increments? We look, it will take a long time, but less likely to skip some important information in between. Now, another thing to mention here is that Q-learning algorithms learn by temporal difference equation, but do we do it all the time? So Q-learning algorithms, Q-learning type algorithms are divided into exploration and exploitation stages. So exploration is a stage when we try more risky actions, or the agents try more risky actions, and sometimes those actions will cause the reward to make a sharp decrease. But in the end, they may help the algorithm to move from a local optima, like the optimization problems, if you think of them. It helps the algorithm not to get stuck in one point, and in the next point, the reward might be even higher. But we can't keep exploring forever because we want the algorithms to converge as well. So that's why there are certain algorithms to design these exploration. Epsilon greedy is one famous algorithm for that one. So with probability epsilon, very small probability, we choose an action at random, which might cause less rewards. And then with probability 1 minus epsilon, we choose the best action, which is the safe option. And in the machine learning literature, first that epsilon was kept steady, and then people noticed that this is not really a good convergence behavior. It doesn't have a good convergence behavior. So most of the times when we say epsilon greedy, that epsilon gradually decreases as we run the algorithm. So by iteration, it does not, it is degraded, or its value is decreased. So this is a very important stage, and one interesting example of this exploration and exploitation was in one of the games. I can't recall the year of it, but in AlphaGo playing machine, it took a risky action. And the scientists, researchers who designed the algorithm panicked for a while, because this is not this is not a correct action. The machine will lose the game. But in the end, it turned out that by doing that exploration, the machine was taking a risky action, but was able to find a better action in the future, and it led the machine to win the game. So one thing about, this is so far so good about Q-learning. It's very interesting. It helps us to understand the interactive learning of humans. It has the exploration, taking some risks. Maybe you may think that there's this convergence thing. Yes, that's a problem. We will talk about it later. But one hidden problem that I did not mention is that when we talk about the classical, traditional Q-learning, most of the algorithms would use tabular methods, which we call as tabular reinforcement learning, where we have to store all the Q values. So when you have a problem, a complex problem that has a lot of states or a lot of actions, the state action space grows quite large. So the algorithms take a lot of time in the working. Also, when the state space is continuous, we cannot use tabular Q-learning. So what should we do? If we don't want to store the entire data set, what is the best thing to do in those cases? What would you do? Well, most of the time we resort to an approximation of these values, like we try to parameterize it so that we can denote it with fewer values. Like you have a big data scattered all around, you just draw a line, regression, right? And then you just store the two values related to that regression curve. Now, most of the time, of course, if you fit just a single line, a regression for the Q values, you wouldn't get a good performance. So what you need to do is you have to find that more trickier curve. The way to find those more advanced curves is by deep learning, right? Or neural networks. Let's go step by step. So the neural networks. Neural networks are actually simple filters. They can be simple filters or they can be very advanced filters. But in the end, their logic is like filtering out some values and leaving us with some boundaries that we can contain the data set. So what we try to do by incorporating deep learning to reinforcement learning is that we would like to get rid of this tabular Q learning methods, or we would like to get rid of storing the Q values in a table and instead denote it by a function of certain polynomial degree or with a neural network, a better representation, and say that this is a function that can generate similar estimates of the Q value. Now, I will come back to this when I talk about deep reinforcement learning, because that is essentially leading us to there. But I will take a step back and start talking about neural networks for those of you who are not very familiar with these concepts. So the idea of neural networks, they started with 50s, 60s when Frank Rosenblatt was studying the idea of perceptrons. Perceptrons are simple devices that have several inputs, a decision circuit in the middle, and then an output. So if you look at it in the simplest way, the output would be 0 and 1, and it will be based on a threshold checking, which should be done in the decision circuit over here, based on the weighted inputs, basically. So all of these links, those arrows, would have a W of weight. This is just a simple perceptron. Now, if you put perceptrons with layers, where the output of one layer would be driving the input of another layer of perceptrons, what we get is a neural network. If we have multiple layers, like one more layer here, another layer over here, we get a deep neural network. So multiple layers of neural networks would create a deep neural network. Now, the nice thing about deep neural network is that it helps us to create compact descriptions. If we had a single layer of neurons, actually, according to universal approximation theorem, we would be able to theoretically model any function that we want, but it would require many number of nodes to be able to do that. So once we do that leveled architecture of deep learning, we get a compact representation of functions. That is the advantage that we get with it. Now, so this is like how the evolution of neural networks was happening almost concurrently when there were advances in reinforcement learning. And another important breakthrough came with recurrent neural networks. So recurrent neural networks started its advancing or started to become popular, let's say, with natural language processing. Because and you know, if you are familiar with the history of AI, there's this famous time that is called AI winter, when, you know, at first there was so much funding, a lot of interest in the area, but then during the Cold World War, you know, people were trying to understand some of the messages sent in between, encrypt them, but the language processing NLP algorithms was not that good at the time. And then there was a disappointment, so AI research sort of got less invested in. But then in the beginning of 2000s, with the discovery or with the development in recurrent neural networks, natural language processing made a leap. And that leap was a result of the capability of RNNs bringing memory into the picture. Because previously, when we look at the neural networks, it's like a feed-forward, vanilla architecture, like nothing goes back, there's no feedback loop. But recurrent neural networks brings that feedback from the previous layers. And with LSTM, with a bit more advanced architecture, what we can do is we can control how much information goes into the next state. So this CT-1 is the memory element or the memory input coming from the previous unit to this actual unit that we're talking about. So it's memory of the previous unit. Then we have the input as the output from the previous LSTM unit being input to this particular unit that we're looking at. So they pass through certain gates, and in the end, they will generate, there's a forget gate and input gate, it would generate another memory input as its output to the future layer, to the forward layer. Now, when we look at this, LSTMs actually can be also very useful for the networks, because some of the features in the networks we would like to remember. So if we are training an algorithm for a wireless network, let's say, and we are using those interactions, some of the interactions would generate such Q values that we would like to actually refer them in the future. So this combined will bring us to a new area, which is called deep reinforcement learning. Deep reinforcement learning is relatively more recent. A fundamental paper was published in Nature by Google DeepMind researchers in February 2015. And after that, actually, this field blossomed in game playing a lot. And also for wireless networking too, we started using this a lot in our research. What happens with deep reinforcement learning is, well, first of all, it is based on LSTM, yes. But if we just use a simple function approximator of LSTM in front of the Q-learning algorithm, there might be some stability issues. So that's why, like, this paper brought in very nice ideas that helps us solve some of the very important problems. And one of them is the experience replay memory, and the other one is the target deep neural network. So this target deep neural network and the deep neural network that we see over here are continuous interaction. They change values, and the target deep neural network is updated. And the experience replay memory helps the Q-learning to derive its values from previous experiences. So all of this will help us to come up with more efficient interactive learning mechanisms for the wireless networks. Now, after this point, I will just take a break of machine learning algorithms because those were like the introduction of the useful tools, like the toolboxes that we need to have in hand. But I'll start talking about 5G, 6G, where are we going with this? And then I'll come back to this machine learning techniques and show you how we apply them for these wireless networks. Um, this picture is a very fundamental picture. I'm sure you have seen it in many times before in other slides or in other papers. It is from International Telecommunications Union, ITU, and it was, I believe, drawn some years ago, maybe even 10, could be even 10 years ago. And this was when, people were first starting to think about 5G, how do we design it, what should be the killer applications. So at that time, three types of applications were, or use cases were considered. But when we look at it from today's perspective, we think that now it should be like a square, actually, because having ultra reliability and low latency at the same time is quite different. But anyways, let's do the historical introduction, and then we'll talk about the details. So the number one service use case for 5G was enhanced mobile broadband. And this is the one that interests humans a lot because that's about game playing, 3D videos, augmented reality, and all that. And one interesting thing, I use this slide a lot in my classes too, and I tell my students, you see where voice stands. This is where wireless communication started with just, people wanting to be able to talk over the phone while they're outside their homes, like not being tied to the landline phone. But now it is just a very small use case for our networks. Our networks, the future networks, will be more about cars, self-driving cars, smart cities, smart buildings, and mobile interactive games. So those, in comparison to voice or simple video, are very straining applications. So enhanced mobile broadband will be asking more throughput for, from the previous generations. If we look at the other corner of this triangle, we have ultra reliable and low latency communications. And over there, we are looking at applications close to 1 millisecond latency. I'm going to say 1 millisecond latency because in 5G first, when it first came out or when we started designing 5G, we said we want to reach 5G. We wanted to reach 1 millisecond latency. But now that systems are being developed, we see that this is really difficult. So around 5 millisecond latency is a reasonable target. And maybe in the 6th generation, we would target lower latencies, close to real time with especially smart factory operations. And then ultra reliability, of course, when you're driving a car and if the brake system of the car is tied to communications, you don't want to lose any information, right? It would be very drastic. And we have also the mission critical applications that are also considered in this ultra reliable and low latency communications, usually known as URLLC. And then the third leg that we have over here is the massive machine type communications with Internet of Things. We are expecting billions of devices to be connected to the networks. Of course, there are other technologies, communication standards that are looking into connectivity for IoT. It's not only 5G, but it would be nice if 5G could grab that portion of the market too and can service users of the smart cities, smart grids, smart buildings, where there would be a lot of devices connected per square kilometer. So all of these are by themselves are very challenging. And when you put all these use cases together, them sharing the network infrastructure at the same time becomes a lot challenging. And the good news is that we have intelligent algorithms now that we can design to help with this complexity. And that's why we are talking about AI-enabled networks for 5G to cope with this complexity. So going back to the characteristics of 5G, in every generation, in every new generation of wireless communications, we start with discussing what's new in the physical layer. And there's usually some modification over there, like for LTE, OFDM was the big thing, MIMO was important, densification was very important. In 5G NR, millimeter wave is the breakthrough technology. So with the advances in millimeter wave, we can use the bands that are higher or in between 24 to 40 or even 60 gigahertz as new bands, which are not used by other technologies. So in wireless, I mean, if you're familiar with the field, you would know spectrum is very difficult. You can't find free spectrum because there's military radios, radar, TVs, a lot of wireless gadgets using the same spectrum. So finding that gap, even the small gap, finding contiguous gaps is really, really hard, but even finding a small gap is very difficult. So with the new structuring of the low band, mid band, and the high band, which is also referred to as millimeter wave, in 5G, we are talking about different spectrum allocations. That's one breakthrough that helps 5G to get that high throughput. Of course, that comes with shortened ranges of the cells, densification, more coordination. Again, why we need AI. But anyhow, let's leave that discussion maybe to the next slides, but talk about other novelties in 5G NR. So we're still using YFTM in 5G, but we have scalable slot durations and scalable numerologies. So the subcarrier spacing could be similar to LTE 15 kilohertz, or it could be higher, going 30, 60, 120 kilohertz. This is the subcarrier spacing of OFDM in communications. So we would need higher subcarrier spacing as we go from higher spectrum values, and 15 kilohertz would be the OFDM version that's compatible with LTE. And in accordance, we have these very short frames, like 2 OFDM symbols, or 17 OFDM symbols that are like jumbo frames, and 14 OFDM symbols that are like jumbo, and 7 is the traditional LTE OFDM number of OFDM symbols we can fit in a frame. Now, those are the things, those are the new things, a couple of the new things that 5G brought. Of course, at the core, we have service-based architecture. At the coordination side, there's lots going into it, but I won't really do a very deep dive onto those things. Rather, I will talk about what's going to be for 6G, how we are designing 6G from with the vision we have today. And then I will move on with the works where we combine machine learning with some area in 5G. So when it comes to 6G, the vision is to have 6G in 2030, because that's the regular cycle of the wireless networks. Every 10 years, there's a new generation that comes with strong technologies. And the research of developing these technologies starts now from today, so that we are ready for standardization when the time comes. And usually it's like an evolution. So it's not like we stop, we say, okay, 5G is done, we forget about it, we start thinking about new things. No, there are certain things that we started working on 5G, but they were not mature enough. So they could not go into the standards. So we keep developing them as researchers, we keep developing them, hoping that they may be a part of the future standards. Terahertz communications is, for example, one very interesting and hot area. Although I have to say, even communications in the millimeter wave band is very challenging. So let alone terahertz, it's quite challenging. And from the tests now, it's just like more like a preliminary study. We don't know if it will work or not, but at least for sensing, navigation, it might have some usability. But like a mainstream of communications, it's still a question mark. NOMA, some of you might have heard about NOMA before because it has been around for some time. It is the non-orthogonal multiple access technique. It was considered for 5G, but was not very mature at that time, so it might come back in 6G. Efficient use of unlicensed spectrum. This is again a topic studied in LTE, 5G, and will be important. because, I mean, spectrum is scarce. We want to make the best out of it. If there is ISM bands that are not being used at that moment, why not use them? Or cognitively using other spectrum. These are all, ongoing studies. Then another very interesting topic is on aerial networks, drones. So up until now, I mean, we have our base stations sitting on the ground or at least on top of a building. But in the future, there are opportunities and a lot number of research going into that area to make it possible that there will be flying base stations. Those base stations could be sent over to the hotspots where users, either there are too many users or they are doing too much bandwidth intensive jobs like uploading computations and stuff like that. And then another type of communications, a physical layer technology, visible light communications, is also, it has been researched since some time. I have some works in that area too from a couple of years back. It is an interesting area, of course, because when we talk about light or photonics or light-based communications, it is outside the RF range. So we don't create any interference to RF, because in RF, in wireless terrestrial communications, most of the problems arise from interference. But imagine like you can find something, some band, like the visible light, that would not interfere with the others. So in that case, of course, there's the big problem of designing transceivers and receivers that would not disturb the human eye, plus that can encode a lot many information and be as efficient as the other RF type solutions. So these are still challenges visible light communication researchers are working on. Another newly emerging area is intelligent metasurfaces. Again, a very hot topic for today. And this is about being able to use some surfaces that can change its characteristic and act as an antenna, so reflect the rays to increase, to basically provide repeater capabilities to the network. But different parts of the surface, or a big antenna, you can say, can provide different capabilities so that they can have low or high reflection capacity. And the last but not least is, of course, dear to my heart, is the AI-based network optimization. So this is where we do a lot of research and contribute to the next generation of networks. And it is sometimes called as network automation, automated networks. These are all not the same, but similar concepts, trying to make the next generation as least dependent on humans as possible. So we don't want the wireless engineers to go to the towers to make some adjustments. We don't want people to spend hours looking at failure maps and to try to figure out how to, reduce interference, or we don't want threshold-based, very simple algorithms that works for a couple of base stations, but that would not work 100 base stations that are working in the same area, like coordinating interference altogether. So 3GPP with self-organized networks, SON, started this actually. So this is like the ancestor of this AI-based network optimization by trying to do a couple of things automatically, like PCI configuration, putting up a base station and having the full configuration sorted out by the base station kind of things. These are done. But when we talk about AI-enabled networks, we talk about a higher level of automation where the network will not only self-configure, but also self-optimize. So yes, I already started talking about this. Yes, SON came with 3GPP, but then a question might be, why do we need that much of an automation? That I can talk about maybe a bit more. With the millimeter wave, the cell sizes are getting smaller and becoming directional because of the beamforming feature. So their coordination is not that easy. We are talking about a massive number of devices connected. We're talking about massive MIMO, number of antennas. We're talking about MEC infrastructure serving for resource-limited devices like IoT devices, additional computation being available and devices accessing through the wireless network. We're talking about multi-access edge computing. We're talking about virtualized RANs, which are interesting topics that my group is doing research on a lot, like the ORAN architecture, the future radio access networks, where multiple vendors, multiple protocol stacks will come together and self-organize and start working together. And then slicing, of course, this has been an area that has been worked a lot, but there are still open research issues there, and automation is an important part of that as well. So in the end, we want to have, automated decision-making capability in the wireless networks, and it is considered like one of the big things in 6G, one of the big enablers of 6G. In our research, what do we do? So this is one of our papers from 2019, where we identified the challenges, opportunities, and open issues in AI-enabled networks. So this is like looking at the run side of things and discussing how do we do fair access with unlicensed bands? How do we do beam alignment, beam management in 5G? And this is one of the works I will talk a bit more. And in the second part of the presentation, you'll hear more about those. And then resource allocation is one of the fundamental problems that my research group works on. How do we tackle the scalable neurology of OFDM in 5G? How do we allocate resources to eMBB and URLLC users so that their performance, both of their performances, are not degraded? And then finally, what can we do for the smart city infrastructures, smart grids, smart homes, smart health? How can 5G help with these technologies? So this is like the big picture. Now I'm going to just focus on a couple of sub areas, and one of them is resource block allocation. So as you might know, resource block allocation or resource allocation in general, has been a problem in 4G. It is still a problem. It is a research problem in 5G, because we have limited amount of users. We have limited amount of resources, and we have so many users who are trying to get some share of these limited resource. And that resource on the RAN part of the networks can be frequency-based. So the subcarriers, how do we distribute a bunch of subcarriers? At which time slot we do that? So the time and frequency allocation, and also at which power level should those resources be used. So before we get into the details of this, I want to just, wear my professor or teacher hat and explain what resource allocation is in very simple terms. So in 5G, we have flexible time slots that can be 2, 4, 7, or 14 OFDM symbol length. And we have subcarriers on the frequency side, which can have different subcarrier spacing, which translates into different numerologies. Numerology 0 is equal to LTE, 15 kilohertz subcarrier spacing, as we mentioned before. So each time users have traffic in the queues of a base station, the base station scheduler will go and try to make an allocation. Every TTI, every transmit time interval, we will try to identify, let's say, who gets this gray spot, or a combination of them, a resource block group. Who gets, because it's very challenging to do it in small timeframes, who gets a block of these resources. And depending on at which time a user gets to be scheduled, their delay will be impacted. If they wait too much in the queue, then, for example, if they are URLLC, they will experience a very bad performance. If the users are eMBB type, they would like to get the best frequency resources. Like over here, every subcarrier is different. Because of the propagation properties, because of the interference imposed on them, every subcarrier would have a different performance. So a bunch of subcarriers are grouped together, 12 in LTE, for example, to form the resource group that is given to a user. So even in this 12 subcarriers, for the eMBB users, because they're going to ask for high throughput, we want to bundle up good subcarriers together. So base station, by looking at the feedback from the user, where the feedback comes as CQI, channel quality index, will determine every TTI which resources to give it to each user. Now, obviously, when doing this decision, some users will be in conflict because they are fighting for resources. So URLLC users would like to have low latency, high reliability. eMBB users would require high throughput. So if we give the best channels to eMBB users, they'll be happy. But then if we don't schedule URLLC users, we keep them waiting in the queue, they'll be unhappy. So we should allow URLLC users to puncture some resources, to steal some resources, do their business quickly, and get out of the way of eMBB users. So there are many, many algorithms, scheduling and, excuse me, scheduling and resource allocation algorithms. Some of them use optimization, but optimization is very hard to do in real time. And also sometimes problems are very complex and NP hard, and we can solve them. So in our approach, in this paper that we presented in GlobeCom in 2019, we proposed a Q-learning based algorithm, and we called it low latency, high reliability using Q-learning LLHRQ algorithm, a long name for an algorithm, but anyways. So what this algorithm does is that it's, first of all, our goal was to use a simple Q-learning algorithm that would not cause too much long working time. And if you recall what I said at the beginning about tabular Q-learning methods and their advantage, state space explosion, now you can understand why we would like to have fewer number of states. So we designed our problem such that we have a desired state and an undesired state. The desired state that the average SINR of the users are above a certain threshold, so that's S0, and other states are called S1. So the agent is forced or encouraged to go to the desired state. This encouragement is done by the reward function. And the reward function is also responsible for encouraging the agent for incurring less latency. So the first of all, the subcarrier selection part, the good subcarriers are selected based on higher SINR values, average SINR being higher than the threshold value. And then the reward itself is associated with the waiting time of the packets. So we have over here average SINR and here the maximum queuing delay. So we want to make the maximum queuing delay as close as possible to 1 millisecond, and we give a partial reward as it approaches to that value. But if it's beyond a certain value, then it is, if the average SINR is lower than a certain value, then we get a penalization. So there's a penalty minus reward, and there's a partial reward given to the agents. So this is a simple scheme, and it had to be simple because tabular Q-learning would make the state space grow exponentially. Plus, we don't want an algorithm that takes very long to converge. But eventually, we're going to discuss that convergence. It is not very easy to reduce the convergence length. So in these type of algorithms, reinforcement learning algorithms, we usually consider that the training is done offline. And we look at the results once the training period is over. So from these figures, we can see that the proposed algorithm, especially for higher load values, performs much better than the traditional, a modified version of a traditional proportional fair algorithm. So that PPF was proposed in a recent time than our proposal, and it was giving priority to URLLC users, or it was adding the priority mechanism to proportional fair by giving higher priority to URLancy users. But over here, by using a reward function, we implemented a similar idea, and we were able to show that the performance of latency is better by LLHRQ when the load increases. Now, going a bit, forward in time and looking at more recent works. So after, looking at the resource allocation problem, one interesting problem that we came across was beam management or interference management between the beams and doing resource allocation jointly. So imagine we have a millimeter wave network. So the cell towers are generating certain beams at a certain beam width, and they are covering several users. So these users, like the ones over here, they have to make a decision whether to get connected to this base station or to this base station, depending on the interbeam interference, interbeam intercell interference. And then once they are associated with one base station, we need to do resource block allocation and power allocation. So in this work specifically that was presented in last year's ICC, we tried to improve the sum rate of the network that was using NOMA. So different than the previous work that I described that was using OFDM. In this work, we focused on NOMA. We have beamforming antennas. We have users with the opportunity of connecting to multiple antennas. And because we are using NOMA, we have to be careful about the power levels because the users will be using successive interference cancellation techniques. So for that, we used Q-learning again. And our agents are G-node Bs, or the base stations. This time, our actions have two dimensions. Delta is the first dimension, where it represents the association of the user. So it's whether to associate to G-node BA or G-node BB or another one. And then another decision, an action that needs to be taken is the power levels of that user. So what would be the power element? Again, we have a simple definition of states because we don't want to explode state and action space. Our actions a bit varied than the previous ones, so that already doubles the memory complexity of the schemes. So we look at the average SANR value and see if we are in the desired state or not. And because we look at sum rate, here reward is also simplified. We are not looking at latency. We are just checking if we are at the desired state. If we observe average SANR above the threshold value, we give a reward of 1. Otherwise, we give a reward of a penalty of -1. And with this, we compared this scheme to, again, another scheme in the literature, and we show that our sum rate can show 30% improvement for lower values and 33% improvement when we go to higher loads. And this is in comparison to a uniform power allocation scheme. So when we don't, do the power allocation intelligently. Now, there is one thing I want to show and discuss. So whenever we do, of course, research in this topic, we look at the convergence. Previously, I did not show because I don't want to show all the results. You can refer to the papers, but I want to start the discussion about the convergence because that's an important thing to be cognizant of. So when we look at convergence, we saw that we can get convergence like around 2500 TTI, which would be too high if we were, starting all these schemes from scratch online. When users come, the base station boots and it starts the training. But we considered that all of these can be done in an offline mode. But still, if we were able to shorten that period, that will allow us to bring base stations alive faster. Plus, if there's a change in conditions, reconvergence would have been faster. So in our team, we started thinking about that, and we developed a couple of techniques, which I will touch upon very simply, and then my PhD student, Metat El Sayed, will get into the details of it. But before we move into that, I want to talk about another recent work that we did in GlobeCon 2020. So in that case, we considered about, again, beamforming antennas, millimeter wave antennas, several users under beams, again, association problem. But we complemented our schemes with a DB scan mechanism, which is a well-known algorithm for clustering, but we modified and made it an online version. So as the users are mobile, they are put in clusters for the beams. And once they are in a beam, they are considered to be associated with that particular base station. And within that particular base station, this time we use deep reinforcement learning for resource allocation. So basically, we try to find the users that are geographically close to each other and that can be covered by a single beam. And DB scan helps us do this and helps us find the least number of beams, because otherwise, beam management would be an issue. So we cluster the users to make them associated with a certain base station, plus we allocate least number of beams to control the interference. And then after that, LSTM-based deep Q learning is used to perform the resource block allocation, which is, one of the techniques that I referred at the very earlier parts of this presentation. So for this scheme, we look at latency and sum rate, and we were able to show that in comparison to another recent scheme from the literature, we were able to both reduce latency. So the red curves are the DQ DL, the DB scan-based deep reinforcement learning technique, and the blue ones are the KPPF. That uses k-means for clustering and priority-based proportional fairness for resource allocation. So we were able to show that if we use DB scan for clustering, we can achieve more superior performance. Plus, instead of the priority-based proportional fairness, if you use deep reinforcement learning, we get better performance in latency plus in some throughput, especially when the loads, offered loads are increasing. So up until now, this is like a short summary of a couple of works we did in this area for improving network performance. Then, as I said, convergence, that's a question mark that has been in minds for a long time for us and for many researchers. We said, can we do something for convergence? There we resorted to the idea of transfer learning, and this work is really dear to my heart. I'm going to show like the paper, the related work that we did later on, but this is the general definition of transfer learning, where we have some tasks, some data sets and tasks that an agent learns. And then when we have the knowledge transfer between the agents, learning from data set, so this is traditional learning, this is transfer learning, learning from data set number 2 becomes much easier because there's prior knowledge given from an agent. So transfer learning has been popular, has been known for supervised learning for many years, and this is what I'm describing here. But transfer reinforcement learning is a bit newer area, but it has been, of course, discovered, studied in terms of robotics in other literature, but we applied it to wireless networks for the first time. So when we do transfer learning, task mappings becomes very important, which I will touch upon very briefly, and then Metat will talk about in details. So in our paper, which is published, well, it was accepted in December, so it's an early access. We don't know the numbers yet, the issue numbers. But in that paper, transfer reinforcement learning for 5G and R millimeter wave networks, what we did was we designed to have some expert nodes with working with non-millimeter wave. So they have this huge coverage area. They learn user cell association. And then we have the learners which try to transfer this information into beam-based association, plus they're going to do they're going to do resource allocation. So with this one, we proposed a we proposed a transfer reinforcement learning algorithm. I won't get into the details of this formulation. You're going to see them more details in the next part of the presentation. But just that for expert G-Node B, we have a certain learning mechanism, a rewarding mechanism. For the learner G-Node B, we have a certain learning mechanism. So when we look at the convergence, we see that some gains can be achieved. So this is the convergence curve for the G-Node B, the expert G-Node B. And these are the convergence values or convergence plots for the learner G-Node B. For us, learner G-Node B is important because we want to say that after a certain point, we will have to like cut off the learning and say, this is when we have the convergence. So there are a couple of things here. So as we can see with transfer learning, and by the way, the comparison is done by Q-learning. So if the learner G-Node beats were not transferring any knowledge, they were starting to learn from scratch by themselves by using Q-learning. So they converge to lower rewards, that's one thing. And then their convergence is taking much longer time than the transfer reinforcement learning. So we can consider transfer reinforcement learning to be converged somewhere around this time. But then for the Q-learning, there are still some variations. And it's also important to make sure that the performance is also better. And in our T-Wireless paper, we showed that, we compared the performance of TQL with a Q-learning method, with a BSDC method, where the BSDC performs the disjoint user cell association and the clustering, and a baseline algorithm. And we show that our algorithm for fixed nodes can achieve comparable performance, and for mobile nodes, for mobile cases, it has better performance. So yeah, these will be covered in detail later on, but let me wrap up my talk with a couple of remarks about AI and wireless networks. So I see this era, I see these times as the AI spring, because in many areas, actually, AI is receiving a lot of attention, of course. It is not summer yet, because we haven't found out the methods, the techniques that are ready for prime time. It would be misleading to say that we have all the techniques, come on, let's go, let's do it, we can do it now. We have to work more on the machine learning techniques. But the nice part is that they are very promising. Networks are becoming more capable of or more allowing us to do AI techniques, like they are becoming more software centric. We have distributed computation at the edge that allows techniques like federated learning to be used. We have the segregation at the frontal, at the run side. So all of these are coming together and giving us more opportunities to apply AI and develop more advanced AI techniques. So it's not just only taking one AI technique from general machine learning domain and applying to wireless. We also have to work a lot, like the design of these algorithms take a lot of time. But once you are able to do that, then you can reach to data-driven decision-making, which is coming like the mainstream approach needed for wireless networks. Now, as I said, there are challenges. That's why the algorithms are not ready for prime time. Convergence is something important. Something has to be taken care of. Scalability is important. Like we usually talk about fewer agents, but when we scale it to hundreds, thousands of agents, then we have to check the performance. Another problem is lack of standardized training sets, or even lack of training sets. The AI and machine learning area, their fundamental developments, their advances was made after some NLP and computer vision data sets were made available. But in wireless, there are several efforts for this, but still we are missing a full-fledged data set. And then distributed agents. Networks are distributed systems. Imagining that all information for decision making to be existent in one central location would not be realistic. So we have to have agents that can work in distributed environments. And another challenge is sometimes in networks things work pretty well, but then there's one really bad event that kind of throws out all the estimations. And how do you learn the rare events? Because training, like in reinforcement learning techniques, you have to train your mechanisms over similar scenarios. But when there's a rare event, how are you going to train your mechanisms? Or when you're using supervised, unsupervised learning techniques, how are you going to detect those rare events? Those are the challenging problems. So yeah, I'm almost at the end of my talk. And of course, behind every good research, there is excellent, bright students who are working very hard night and day. And this is my team of researchers. We are 14 right now and growing every day. And they work on, of course, AI-enabled networks. They work on smart grids, enabling machine learning techniques for the smart grids, and doing lots of interesting research. And of course, again, research won't be possible without the funding, generous funding from agencies. NSERC is our funding agency in Canada that funds our lab. NSF is the funding agency in the US, which we receive also funds from. MyTax is a Canadian funding agency. Ontario Centers of Excellence with its Encore programs, Encore 5G programs are funding our research, and Natural Resources of Canada, Natural Resources Canada is funding some of our research in smart grids. So with this, I would like to say thank you for your attendance, for your attention, and I'll be online for answering your questions. But if you cannot ask your questions at the moment, you can always send me an email and I'll try to respond to your emails. Thank you very much.